Okay, thank you very much. So the result that I'm going to present has nothing to do with logic, but it's just what it is. Yeah, so it just says that every L group can be embedded into an L group whose automorphisms are in it. But the way we got it actually went through logic, and it's in some sense it came to be as a byproduct of something, or a side effect even maybe of something else that we wanted to do, and we did with a colleague Michal Botul from Czechia. So when we did that, then we realized, well, that it's actually not quite a new result. It's we didn't know that, but indeed we did reprove an old result. I go back. Old result, but in some sense our proof is better, at least insofar as it does not use any set theoretical assumptions. Or any special set theoretical assumptions. So, all right, here we go. And the lattice ordered group or an L group is a lattice and a group on the same universe. And the group operations and the lattice operations, does it point? No, it does not point. It doesn't matter. They have to behave nicely with respect to one another. So that means that the multiplication distributes both over meet and over join. And then, like in group, you have this fundamental Cayley representation. In L groups, you have an analog of that in the form of Holland representation. Namely, it says, just like Cayley, well, there are two ways of presenting, of talking about Cayley theorem. One way would be that every group is embeddable into a permutation group. Then this is a perfect analog, because then Holland's theorem says every L group is embeddable into an L group of order preserving permutations on a chain. So that's a perfect analog. On the other hand, in the Cayley case, these permutations actually are, they come from the automorphism group of the group. So you can, in another way, you can express Cayley as by saying that every group is embeddable in its own automorphism group. Here, it's certainly not the case. For example, if you take the integers as an L group, its automorphism group is trivial. So no way you can't do that. And it will play, it will play a role. Because what? Okay, well, perhaps I'll come to that. So here's the theorem, proved, as we realized, by McCleary in 1973. In fact, it was proved in the course of proving something else, but the theorem is this. It's just a result that I am going to prove in a different way. That proof goes by playing around with Holland representation, and it relies on some set theoretical assumptions. Doesn't matter exactly what they are, but it's something assuming GCH, so it's some sort of heavy set theoretical machinery. Now, so that this is the I can't point that. This is where we're going, and now the logic detour. How we get there. So first, observe that L groups are in fact term equivalent to a variety of residuated lattices, and residuated lattices, as the logicians here will realize, are closely related to certain, well, they are say, algebraic semantic of certain non-classical logics. So this is the beginning of the logic connection. They can be presented as residuated lattices. So you just replace the multiplication by two divisions, and then you add one equation, and that's what they are. But there is another connection, and this other connection goes, and I somehow by accident, I am in a very good moment. I'm speaking a very good moment of the conference, because just before me there was a talk about MV algebras, and it also mentioned perfect MV algebras, and that's just what I need, because here's another logic connection. So first, if you have an L group, then a strong ordered unit is an element, positive element, such that for every element of an L group, some power of that element U exceeds that element. Now, you can take the interval between the identity element of the L group and the strong ordered unit, and just take that interval. This interval is a sublattice. The lattice operations are okay within that interval. And then for let's say for the divisions, for the slashes and multiplication, you just truncate them in the natural way to within that interval. What you get is something that's known as a pseudo-MV algebra. And the pseudo-MV algebra is a non-commutative generalization of an MV algebra. And an MV algebra is what you've seen. And what? And and if you do what I've just described, this interval to a abelian L group, then you get an MV algebra. Yep. Well, this is some blah blah blah. MV algebras are popular. They're used for this and that, and in this area and in that area. Pseudo MV algebras are really what you get if you want to give up commutativity, but you don't want to give up anything else. You think about it, you get a definition, and this is exactly what pseudo MV algebras are. And now back to the connection with L groups. So this starts with Chang. Chang in I don't know, sometimes before I was born, so it must have been like 200 BC, something like that. The 50s, I suppose, 1950s. Yeah, it was. Chang realized that connection between intervals in abelian L groups and MV algebras. And then time passed, and then Mundici realized that you can go the other way. So you can start with an MV algebra and reconstruct an L group such that if you take that proper interval of that L group, you recover the MV algebra. And that correspondence going there and back is actually functorial. So you get a categorical equivalence between the two. Classes, that is. If you think about them as categories, there would be abelian L groups with a strong unit, with homomorphisms, and MV algebras as a variety. So MV algebras with homomorphisms. And turns out that you could do the same in the non-commutative case. So you take pseudo-MV algebras as defined by Georgescu and Iorgulescu, and then Dwureczyński realized. So and they had them as these intervals. And then Dwureczyński realized that the Mundici correspondence, the Mundici functorial correspondence, generalizes to the non-commutative case. So you have the categorical equivalence between those pseudo-MV algebras and L groups with a strong unit. All right, now this is where we entered into the story. First of all, we need this thing called perfect pseudo-MV algebra, and perfect is exactly what Ramaz told you. So it's perfect is something that looks like this. It has the top here, the bottom here, and it sort of splits into two parts. This is a filter, this is an ideal, and every element of the filter is above every element of the ideal. So in other words, you have a homomorphism into the two-element Boolean algebra here. And it's not just that you have that homomorphism, but this order is that strong here. So this is what in the theory of MV algebras that would be infinitesimals. Yeah, this is this bit is what Ramaz called the radical, and this is the co-radical of the dimension. This is what these are. Now, we realized while we were looking at these perfect pseudo-MV algebras because of some other connections with some other work, but we realized first that they are nice as a category because they are almost a variety. But this is not so important. I mean, it's not important at all, but it's just interesting. But we also realized that there is yet another categorical equivalence here in the background. Namely, if you take the perfect pseudo-MV algebras as a category, not as a variety, so with those operations that I mentioned here. So with homomorphisms, but with homomorphisms between perfect. Then they are categorically equivalent to L groups with a distinguished automorphism. All right, so how this goes? This just goes as follows. You take your perfect pseudo-MV algebra, and you realize that there are two L groups somewhere in the background. And so here's your perfect pseudo-MV. In one way, it is an interval in an L group. So there is a big L group over here. Who knows how it goes? That's a big L group. It sits inside that thing. On the other hand, this is perfect. So because this is perfect, it doesn't quite look like this. It looks more like that. And then there is a further result that says that this bit here, so the filter is actually a negative cone of another L group. So there is an L group here such that its negative cone is precisely that one. So we have these two L groups here. They are the purple one, which gives you that original pseudo-MV as an interval here, and the black one such that the co-radical negation of the radical of the pseudo-MV there sits here as a negative cone. And then furthermore, there is a connection between the two. Namely, the connection is such that if you take this red pseudo-MV, then you have the lattice operations, you have the slashes, but also you have two negations. It's not non-commutative, so that there are two different negations. But if you do them in, well, first one and then the other, you realize that this gives you it does give you an automorphism of this pseudo-MV, but it also extends to an automorphism of the purple part. And in fact, it's, well, all right. It boils down to the fact that that this big thing, can be represented as a special semi-direct product of the integers and the h, which is the black one. Now once you, so this is where we got with our results that were sort of logically motivated about these perfect pseudo MV algebras. But then you step back, you look at this. I mean, we didn't have that picture in mind when we were doing that, but now we do. And then you realize that this doesn't really have anything to do, well, I mean, it has something to do with this pseudo MV algebra, but you don't need it really. Yeah, it really tells you that that if you take an L group and a distinguished automorphism, then you can embed that L group into a bigger one in a rather special way. Maybe you construct that G this way, and here's your automorphism. This automorphism gets killed in a sense that this was just an arbitrary automorphism of the black one. But now it is actually in the bigger L group. It's inner. It's given by it's given by a conjugation. So here's a definition to flesh it out. This is just the definition of that special semi-direct product. This here. And you see that it uses the lambda. This is what makes it inner. And our two lemmas. First lemma is obvious. Now you pick an L group, you pick an automorphism, and then in that big L group that extends L, the automorphism lambda extends to an inner automorphism. Well, I mean that's just this is what it is. But then this is, in some sense, this is how that big semi-direct product was constructed. But then, more importantly, this other lemma tells you that this way, how do I say that? You don't get any, all right, you extend the group, but you don't get any more automorphisms. You can lose some, but you will not get more. Because if it so happens, so say you do this, you do this, and now you look at the automorphism group of that. Now, if there is some automorphism there that restricts to something here, then it must commute with the lambda. So you can't get too many automorphisms. You don't get any new automorphisms. You can get fewer automorphisms, but you don't get any more. And this is good because that tells you what? That immediately gives you an idea of iterating the construction. Yeah, you start with your group, pick an automorphism, embed, make that automorphism inner. Well, you have a bigger L group, and then maybe some automorphisms there that you missed. Well, do it again, and then do it again, and then do it again. And the fact that you don't get any new ones tells you that this procedure will terminate somewhere. Well, of course, transfinite induction in general, but you will get to the top. And this is it, basically. And this is an example. The simplest example that there may be, because if you take just the integers, then you don't have any non-trivial automorphisms. So here's z squared. Z squared, the order goes from left to right. The only non-trivial automorphism is just flipping the coordinates. All right, what do? You do this. You take Z copies of Z squared, order them lexicographically, and then define the multiplication as you would in the definition there, using the lambda as the flip. So when you go over this calculation, say what we are doing, we're taking an arbitrary element from here, right? And we're conjugating it by this element here. Or rather, sorry, yes, that's right. And then you calculate blah, 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 blah. And here you come to this point, and this is just your automorphism. So that flips the coordinates, you get the coordinate flip, blah, 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 and you'll see that in the end, what this conjugation does is exactly what your automorphism does. So that way you get it as an inner automorphism. And then the rest is simple. You just have to iterate. And then there is an inductive procedure. So you have a base step, blah, blah, blah. You enumerate the automorphisms. You formulate the inductive hypothesis as you typically would. You formulate it a bit stronger that you want because this is easier to prove. You know, it's often like that. Yeah. You want to prove something by induction. You want an inductive hypothesis that is a bit stronger that you really need for the theorem, but it's better for the proof. You do that, you iterate, you take care of the transfinite induction, and then you take the union at the last stage, and then you get what I announced. And now the bonus is there are two bonuses. This construction gives you not only an embedding, but actually L embeds into the G as a normal or convex normal subgroup. So the best you can get. And the cardinality. You started with an L group. So, and all the stages were really countable. Yeah, you're just doing something by, well, multiplying by Z. Well, so this doesn't lift the cardinality beyond what's obvious. So of course you have to have some automorphisms to start with. You will get fewer, but well, I mean, not more than that. Not more the cardinality of L, whichever is greater. That's it. And thank you very much.
It was the day that we went to
Burley Head.